So, welcome to workshop number 5. Now what we're going to be doing today is talking about integration, and particularly let's start with the basic question, what is integration? And then we'll deal with why do we bother with it. In integration, if we have a graph, I know, velocity times time, and I put something like that in for no particular reason, V is equal to, I don't know, t squared minus 5 plus, yep. So anyway, if I have some crazy formula like this, if I would integrate, what is this? This area under the graph actually physically represents something. Now, area is equal to base times height, which is equal to, base is going to be time, the height is going to be velocity, so that's going to be distance. So the distance is equal to velocity times time. So if I would integrate that velocity, that would give me the distance. So if velocity is equal to that, if I go, I want to find distance is equal to integration of velocity dt, and away I go. If I then, now when I integrate it, what that does is this creates a formula that tells me for any value of t what the value of what's this here, t is equal to t third minus, well, it's at 5t. This tells me, this creates a formula that lets me know for any value of t what the distance travelled is. So I stick in a value of t, it tells me the distance. Isn't that cool? So that's what we're doing. When we're integrating, we're trying to make a formula that tells us the area under the graph from 0 to that point. There's a few things that you have to work out, but there's lots of areas which are useful. Now, one thing you also have to remember is integration is the opposite of differentiation. And what that means is if I integrate something, so say I have x squared and I integrate it, that gives us, what's that, 1/3 x cubed. And then if I differentiate that, 1/3 x cubed d over dx, that should give us x squared. So if I integrate something and differentiate it again, I end up with exactly the same place that we started. That only took us about, what, 3,500 years to figure out, so maybe 4,500 years to figure out. It's one of the great works of people like Newton and Leibniz and the others that were working at the time. So, but why do we do this? Well, when we have integration and when we have differentiation, these are a very powerful tool in the toolbox of the engineer. I mean, we're not going to teach you this stuff unless you're actually going to use it, and you will be using it a lot. Partly because we like drawing pictures, and this has got value, and partly because it becomes an easy way to give something with respect to something else, or working out areas of graphs. And let's give you an example of this stuff turns up all the time, especially when you're dealing with things like kinematics, electricity, stress, all sorts of things. Like, let's take a real world example that I was using for my thesis. For my thesis, I had a car body. On it was a spring, and there was a wheel, and in parallel there was a dashpot damper. Well, there was a damper which is variable, and this was going across the surface. Now, what I needed to do for my damper, because it's active damper, I put in an algorithm. This is Carnop's skyhook damper. Force is equal to negative times some constant times the velocity that wheel is going up and down. That's very good. How do you measure the velocity? Okay, not so easy. So there's two ways of doing it. What we can actually do, velocity is equal to dx over dt. So if I measured the height, bounce up and down, bang, 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 then I can measure the velocity. while that was technically possible, it was not really feasible for my project. Another way of doing it though is to go velocity is the integral over acceleration dt. So if I imagine a graph and I have the acceleration here, I have the time here, and I want to measure up this area, velocity equals area times time. So velocity, is equal to acceleration times velocity is equal to the integral of acceleration. So basically, if I split this up into lots of little bits and add them all up, but I'm not going to do that real time. What I was using was a program called VisSim, and I was also using Simulink. These are a couple of computer programs you'll probably end up using, and it's a graphic interface computer program. It's like wiring up electronic circuits, and there's this little block that's called int, and this does all the integration for you. So it will solve it numerically. It will break this up into small slices and do the adding for you. So basically I had my signal, I had my acceleration come in here, I had my end block, and out back of that came velocity. So basically I had my signal here from my I had a little accelerometer here which fed into the computer. Accelerometer goes in there, goes through integration, I get velocity out, and then I can control that. So that's one place you're going to be using it. You're going to be using it modelling. These are used a lot in modelling, especially for dynamic systems. Same for differentiation. You'll be using it for for control systems, real-time systems. So the calculus, these things here, integration and differentiation, are new ways. A lot of the time, they're just new ways of thinking about what you've already been doing anyway. But they're putting them into a nice mathematical notation so that we can use them. Okay, there's also a couple of other, so basically engineers, physicists use this stuff to describe reality, and scientists use these calculus to describe reality. In fact, Newton came up with it to basically aid his physics. Engineers use this to build stuff that will actually be useful in the real world. But that does lead us to one small problem. So you cannot integrate everything. Well, we can try it. Like, let's take a loop. Here's some more research of mine, which I actually did again for my thesis. If you have a loop of wire and it's circular, and you want to measure the magnetic field on that wire at a certain point down the axis, that's actually quite easy. We use the Biot-Savart law, and it integrates I times blah blah distance blah over r squared blah 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 blah. There's mu naught in there over d little. So basically we integrate the magnetic field, break it up in little chunks and go all the way around here. So we can solve that analytically. What I mean when I say we solve it analytically, we can actually make an equation that will do what we want it to do. But what happens if you want to find out what the magnetic field is here? This is no longer symmetrical. The distance from here to here is different than the distance from here. This example, because we're measuring the centre, distance is always going to be the same, but in this case it's not the same. How do we use that? Well, we use something called elliptical integrals. And at the moment there is no analytical way of solving an elliptical integral. We cannot solve them. If you ever figure out how to do it, let us know. Write it up in a journal paper, get your name out there. Mathematicians and physicists will love you forever. But, so how did I do it? Well, I did it numerically, and that's what we'll often use as engineers. If we can't do it analytically, we'll do it numerically. So what I did is, instead of doing it analytically, I basically did worked out at every single point, edited up myself. Instead of trying to get this formula to do it, I recognised I was going to have to do each individual bit. But we'll do some more on that later. So anyway, the takeaways I want you to do is when we're dealing with graphs and things, areas of graphs are important. Calculus allows us to work out the area, makes a formula that allows us to work out the area of the graph at any point. And once we've got, and together with integration and differentiation, this allows us to actually write and see mathematics in a different way and allows us to communicate with other engineers, because in many ways maths is a language, and we've agreed as engineers through things like the Washington Accords and other agreements with other universities and other engineering organisations around the world that all engineers should basically speak the same language. And what some of those elements of this are going to be integration, differentiation. So that means hopefully if you see a journal article from somebody from France or China or Russia or America, you should at least have the same math between all of you. And that, if nothing else, should allow you to communicate quite effectively. So anyway, get used to calculus. You're going to be seeing it a lot over the next 3 years. Good luck.